There is a quietness that settles over certain thoughts, a particular kind of stillness that comes when considering the hidden architecture of everything around us. And tonight, I find myself drawn into that contemplative space where the invisible becomes almost tangible, where the building blocks of existence reveal themselves not through noise or spectacle, but through patient observation and gentle wonder. Chemistry is everywhere, in the air moving through an open window, in the pages of an old book, in the glass that holds water, in the water itself, and yet it remains largely unseen, working its quiet transformations beneath the surface of our daily awareness. It is the language that matter uses to speak to itself, the grammar of atoms and molecules, the syntax of bonds forming and breaking in an endless, elegant conversation. I imagine a laboratory late in the evening, not the bright, bustling space of daytime work, but rather a place where shadows lengthen across wooden benches, where glass vessels catch the last amber light, where everything has settled into a profound hush. In such a space, one might sense the presence of something ancient and fundamental, the same forces that have been orchestrating the dance of particles since the universe began, still present, still active, still weaving their intricate patterns. The periodic table hangs on a wall somewhere in my mind's eye. That elegant arrangement of elements, each one a distinct character in the grand story of matter. Hydrogen, the simplest, the first, born in the heart of the universe itself. Carbon, the backbone of the life, the connector, the builder of infinite complexity. Oxygen, the breath, the burner, the partner in so many essential reactions. These are not mere abstractions, not just symbols in boxes arranged in rows. They are the fundamental vocabulary of existence, the letters from which every material thing is written. The iron in ancient meteorites and the iron in our blood share the same essential nature. The carbon in a diamond and the carbon in a pencil lead differ only in arrangement, in the pattern of their connections, in the geometry of their bonds. There is something deeply calming about this realization that beneath all the variety and complexity of the material world, beneath the countless forms and textures and colors, there exists a finite collection of elemental building blocks, 94 of them occurring naturally, each with its own character, its own way of interacting with others. And from this relatively small alphabet, the universe composes everything we see and touch and experience. Tonight, I find myself drawn into this realm not as a student facing an examination, not as someone seeking to master formulas or memorize reactions, but rather as someone standing at the edge of a vast, quiet ocean, content to observe the patterns in the waves, to notice how water moves, how light plays across its surface, how everything connects in subtle, beautiful ways. The story of chemistry is really the story of transformation, of how one thing becomes another through the rearrangement of atoms. It is the story of fire turning wood to ash and heat and light, of iron slowly joining with oxygen to form rust, of grapes fermenting into wine, of flour and water and yeast rising into bread. These transformations have accompanied humanity since our earliest days, and long before anyone understood the underlying mechanisms, people observed, experimented, and learned to work with these mysterious changes. There is an old alchemical symbol, a snake eating its own tail, representing cycles and transformation and the unity of all matter. The alchemists, Those medieval and Renaissance seekers were wrong about many things. They never succeeded in turning lead into gold, never found the universal elixir, and yet they were not entirely misguided. They understood intuitively that matter could be transformed, that hidden relationships existed between different substances, that patient observation and careful experiment could reveal profound truths. In many ways, they were the ancestors of modern chemistry, their smoky laboratories and cryptic manuscripts forming a bridge between ancient philosophy and systematic science. They developed techniques for distillation, for separation, for purification. They created specialized vessels and tools. They kept meticulous records, even if those records were sometimes obscured by mystical language and symbolic imagery. And underneath all their spiritual seeking and their quest for transmutation, they were engaging with something real and profound, the actual behavior of matter, the genuine transformations that occur when substances combine or separate, when heat is applied or removed, when solutions crystallize or vapors condense. I can almost smell the strange mixture of aromas that must have filled those old laboratories, the sulfurous tang, the sharp bite of acids, the sweet, heavy scent of certain metals, the acrid smoke of burning materials, each smell a clue, each observation a piece of a larger puzzle, slowly, over centuries, being assembled into something approaching understanding. But even now, even with our modern knowledge and sophisticated instruments, there remains something mysterious and wonderful about chemistry, something that invites quiet contemplation rather than mere memorization. It asks us to imagine scales we cannot directly perceive, to think about particles too small to see, about reactions happening in infinitesimal fractions of a second, about forces that hold atoms together with invisible yet powerful bonds. And so tonight, I invite myself deeper into this realm, not rushing, not straining, but allowing the story to unfold at its own pace, like a chemical reaction proceeding according to its own inherent timing, like a crystal slowly growing in a saturated solution, adding layer upon layer, building structure from solution, creating order from apparent chaos. The story begins long before there were laboratories or textbooks, long before anyone had conceived of atoms or elements in the way we understand them now. It begins with fire, with that first flame captured and tended, with humanity's earliest encounter with deliberate transformation. Imagine the scene. Tens of thousands of years ago, a group of people gathered around a fire, watching as wood, solid and substantial, becomes heat and light and smoke and a small pile of ash. The wood is gone, transformed into something else entirely. This must have seemed like magic, like a doorway into forces beyond ordinary comprehension, and in a sense, it was. Fire became humanity's first chemical laboratory. In its heat, clay hardened into pottery, giving people vessels to store and carry and cook. Certain rocks, when subjected to intense heat, yielded metals, copper first, gleaming and malleable, then bronze when copper was combined with tin, opening an entire era of human development. The people who discovered these processes didn't understand oxidation or reduction, didn't know about the rearrangement of atomic bonds, but they learned through patient trial and observation. They learned which ores yielded which metals, which temperatures were needed, which techniques produced the best results. This was chemistry, practical and empirical, passed down through generations as closely guarded knowledge. In the Nile Valley, the ancient Egyptians developed sophisticated chemical practices. They created pigments of stunning permanence, blues and greens and golds that still shine on tomb walls thousands of years later. They developed techniques for extracting and purifying metals, for making glass, for creating cosmetics and medicines, for the elaborate process of mummification. The word chemistry itself, some scholars believe, derives from the ancient Egyptian word for their land, chem or kemet, meaning black earth, the dark fertile soil left by the Nile's flooding. This connection feels appropriate. Chemistry emerging from the earth, from the transformation of materials, from the patient work of hands, learning to shape and change the substances of the world. The Egyptians created natron, a mixture of sodium compounds, which they used in mummification and in glass making. They made faience, that brilliant blue-green glazed ceramic. They extracted oils and essences through primitive distillation. They ground minerals into powders, mixed compounds, observed reactions, all without understanding the underlying principles, yet achieving remarkable results through careful attention and accumulated experience. Meanwhile, in different parts of the world, other civilizations were conducting their own chemical explorations. In China, artisans were creating porcelain of extraordinary refinement, the right clay, the right temperature, the right glaze, all had to come together in precise harmony. They were also experimenting with what would eventually become gunpowder, mixing sulfur and charcoal and saltpeter, observing the dramatic reactions when these substances combined. The Chinese developed intricate processes for extracting metals from ores. They created bronze vessels of incredible artistry and technical sophistication. They fermented grains into alcohol, pickled vegetables, made vinegar. All of these processes involved chemical transformations, though the language to describe them would not exist for many centuries. In the ancient Mediterranean world, Greek philosophers began to ask fundamental questions about the nature of matter. What is everything made of? They wondered. What underlying substance or substances compose the vast variety of things we observe? Thales of Miletus, living around 600 years before the Common Era, proposed that water was the fundamental substance, the origin of all things. This seems quaint now, but it represented a crucial shift in thinking, an attempt to find unity beneath diversity, to identify fundamental principles rather than simply cataloging observations. Empedocles proposed that 4 elements, earth, water, air, and fire, combined in different proportions to create everything in the material world. These elements were thought to be moved by 2 forces, love, which brought them together, and strife, which drove them apart. It's a poetic framework mixing physics and metaphysics, but it represented an attempt to understand transformation and change. Democritus, whose name means chosen of the people, proposed something remarkably prescient. He suggested that if you kept dividing matter, cutting it into smaller and smaller pieces, you would eventually reach a point where no further division was possible. These ultimate particles he called atomos, meaning indivisible. He imagined these atoms as tiny, solid, eternal particles, differing in shape and size, and that the properties of different materials arose from the shapes and arrangements of their component atoms. This was an extraordinary insight, arrived at through pure reasoning rather than experiment. Democritus couldn't see atoms, couldn't prove their existence, but his intuition led him toward a truth that wouldn't be confirmed for more than 2,000 years. His contemporaries largely ignored or rejected his ideas, preferring the more elaborate and exoplanetary frameworks of other philosophers, and yet his vision of atoms moving through void, combining and separating, contained the seed of modern atomic theory. Aristotle, perhaps the most influential of ancient philosophers, modified and extended the four-element theory, adding a fifth element, the quintessence or ether, thought to compose the heavenly bodies. He proposed that substances could transform from one to another through changes in their qualities: hot, cold, wet and dry, lead and gold. In this view were different combinations of the same fundamental matter, suggesting that transformation between them might be possible. This Aristotelian framework would dominate Western thought about matter for nearly 2,000 years. It was elegant, comprehensive, and completely wrong in most of its specifics, and yet it served as a foundation for countless investigations and experiments. It gave people a language to discuss material change, a framework within which to organize observations. The practical arts continued to advance throughout the classical period and into the medieval era. Metallurgists refined their techniques, learning to work with iron, to create steel, to alloy different metals for different purposes. Glassmakers achieved new levels of clarity and color. Dyers discovered new ways to extract and fix colors from plants and minerals and certain sea creatures. The production of Tyrian purple, that royal color extracted from thousands of sea snails, represented both chemistry and economics. The process was complex, labor-intensive, and the result was a dye of exceptional quality and permanence. The exact mechanisms of how the chemical compounds in the snail's secretions bonded with fabric fibers was unknown, but the process worked, and that was sufficient. Fermentation remained mysterious and almost magical. Bread rising, grapes becoming wine, honey becoming mead, milk becoming cheese. These transformations happened in their own time, seemingly of their own accord, guided by invisible agents that wouldn't be identified as microorganisms for many more centuries. People developed elaborate rituals and precise methods, knowing that certain conditions favored successful fermentation while others led to spoilage. In the medieval Islamic world, chemistry advanced significantly through the work of scholars like Jabir ibn Hayyan, known in Latin as Geber, working in the 8th and 9th centuries. He emphasized careful experimentation and detailed observation. He described processes like distillation and sublimation with precision. He worked with various chemical substances, acids and alkalis, salts and metals. Jabir wrote extensively, though many works attributed to him may have been written by later scholars using his name. His texts described laboratory equipment and techniques, methods for purifying substances, procedures for combining materials. Much of his work was wrapped in symbolic and mystical language, following the tradition of keeping chemical knowledge hidden from the uninitiated. But beneath the symbolism lay genuine experimental work and practical knowledge. The development of distillation technology represented a major advance. The alembic, a specially designed vessel for separating substances by heating and condensing, allowed for the purification of liquids, the concentration of essences, the separation of alcohol from fermented beverages. In skilled hands, distillation could isolate specific components from complex mixtures, producing substances of unprecedented purity. Arabic scholars preserved and translated ancient Greek texts on natural philosophy, adding their own observations and innovations. They coined new terms, many of which have passed into modern chemistry: alcohol, alkali, elixir, alembic, all derive from Arabic. This linguistic legacy reflects the central role that Islamic scholars played in developing chemical knowledge during Europe's medieval period. The quest for the philosopher's stone became a central preoccupation of medieval and Renaissance alchemy. This legendary substance was imagined to have the power to transform base metals into gold, to create an elixir of life, to perfect matter itself. The search for it drove countless experiments, motivated scholars to spend years in their laboratories, mixing, heating, observing, recording. Was this search misguided? Perhaps. Gold cannot be made from lead through chemical means. Atoms of one element cannot be transformed into atoms of another element through the processes available to alchemists. And yet, the search itself generated real knowledge. Alchemists developed new kopke equipment and techniques. They discovered new substances and documented their properties. They learned about acids and bases, about crystallization and precipitation, about the behavior of materials under different conditions. Paracelsus, working in the early 16th century, challenged many traditional alchemical and medical ideas. He emphasized the importance of chemistry for medicine, proposing that the body functioned through chemical processes and that diseases should be treated with chemical remedies rather than the traditional herbal preparations. He introduced the use of specific minerals and chemical compounds as medicines, mercury and antimony and sulfur compounds. His ideas were controversial and often overstated, but he helped shift alchemy toward a more medical and practical orientation. He insisted on the importance of experiment over authority, declaring that knowledge came from observation and testing rather than from ancient texts. This empirical emphasis, combined with his focus on practical applications, helped lay groundwork for chemistry's emergence as a distinct discipline. The alchemists worked in spaces filled with furnaces and vessels, retorts and crucibles. Their laboratories must have been extraordinary places, filled with strange smells and colored smokes, with substances bubbling and crystallizing, with the constant work of heating and cooling, mixing and separating. The knowledge they accumulated was often recorded in coded language and allegorical imagery, making it difficult for outsiders to understand. Yet within the alchemical community, this symbolic language conveyed real information about procedures and substances. Gradually, through the 17th century, a transformation began to occur in how people approached the study of matter. The mystical and symbolic framework of alchemy started to give way to something more systematic, more openly shared, more focused on understanding rather than simply achieving practical results. Robert Boyle, working in England and Ireland in the 1600s, embodied the shift. He conducted careful experiments with gases, with combustion, with the properties of air. He developed an improved air pump, allowing him to create partial vacuums and observe how substances behaved in the absence of air. He found that a flame would not burn without air, that animals could not survive without air, that sound did not travel in a vacuum. Boyle published his findings openly, Writing in clear language rather than alchemical codes, he emphasized reproducibility, the idea that experiments should be described clearly enough that others could repeat them and verify the results. This seems obvious now, but it represented a profound change in how knowledge about matter was shared and validated. He questioned the Aristotelian four elements, arguing instead that elements should be defined as the simplest substances into which matter could be divided, substances that could not be broken down further. This was a crucial conceptual shift, moving away from philosophical speculation toward operational definitions based on experiment in his book The Skeptical Chymist, published in 1661. Boyle challenged both the four-element theory of the ancient Greeks and the three-principle theory popular among alchemists: sulfur, mercury, and salt. He argued for a more empirical approach, observing what actually happened when substances were heated or mixed or separated, rather than imposing preconceived frameworks. The air itself became an object of intense investigation. What was this invisible substance that surrounded everything, that was essential for fire and for life? Different investigators began to realize that air was not a single pure element, but rather a mixture of different substances. Joseph Black, working in Scotland in the 1700s, investigated what he called fixed air, what we now know as carbon dioxide. He showed that this gas was produced when certain carbonates were heated, and that it was the same gas produced by respiration and by burning. He demonstrated that it was denser than ordinary air, that it extinguished flames, that it could be absorbed by alkaline solutions. Black's work was meticulous. He weighed substances before and after chemical reactions, measuring the changes with precision. This quantitative approach, applying careful measurement to chemical processes, would become increasingly important, transforming chemistry from a primarily qualitative science into one based on exact measurements and mathematical relationships. Joseph Priestley, an English clergyman and natural philosopher, conducted extensive experiments with different kinds of air, or gases as they would come to be called. He isolated and studied what he called dephlogisticated air, a gas in which flames burned brighter and mice lived longer. This was oxygen, though Priestley himself never fully abandoned the phlogiston theory to understand its true nature. The phlogiston theory held that combustible materials contained a substance called phlogiston that was released during burning. When something burned completely, it had released all its phlogiston. This theory explained many observations why metals gained weight when they burned. They were supposedly losing light phlogiston and retaining heavy residue, but it ultimately proved to be wrong. An elegant idea that didn't match reality. In France, Antoine Lavoisier was conducting his own careful experiments, weighing substances before and after reactions with unprecedented precision. He heated mercury in a closed container, carefully measuring the air and the mercury and the red powder that formed. He noticed that when mercury was heated, it combined with part of the air, and the remaining air would not support combustion or life. When he collected the red powder and heated it more intensely, the mercury returned, and the gas released was the same as Priestley's dephlogisticated air. Lavoisier realized that combustion was not about releasing phlogiston, but about combining with this component of air. He named it oxygen. from Greek words meaning acid former, because he believed it was essential for forming acids. Lavoisier's work in the 1780s and 90s established the law of conservation of mass. The principle that in chemical reactions matter is neither created nor destroyed, but only transformed. Total mass before a reaction equals total mass after. This seems simple, but it was revolutionary, providing a foundation for understanding chemical change through careful measurement and balance. He developed a new system for naming chemical compounds, working with other French chemists to create a logical nomenclature based on the elements that composed each substance. This system replaced the confused multitude of traditional names: oil of vitriol and butter of antimony and lunar caustic, with names that indicated composition: sulfuric acid and antimony, chloride, and silver nitrate. This new language made chemistry more accessible, more logical. It allowed chemists to communicate precisely about substances and reactions, to see patterns and relationships that had been obscured by traditional naming. It represented chemistry becoming a true science with systematic methods and clear terminology. Lavoisier also compiled a list of elements, substances that could not be decomposed by any known means. His list included true elements like oxygen and nitrogen and hydrogen, but also some substances that would later be found to be compounds. His approach was sound even if his list was imperfect. Elements were defined operationally by what they were observed to be, not by philosophical preconceptions. Tragically, Lavoisier was guillotined during the French Revolution in 1794, a victim of political upheaval. His contributions to chemistry were deemed irrelevant by revolutionary tribunals, focused on his former role as a tax collector. A colleague reportedly said that it took only a moment to cut off his head. But France might not produce another like it in a century. The loss was profound, a brilliant mind silenced at the height of his productivity. Yet his work survived him. The new chemistry he had helped establish continued to develop. Other investigators built on his foundations, exploring the properties of elements, studying how they combined, measuring the proportions in which substances reacted. John Dalton, an English schoolteacher with a deep curiosity about the natural world, proposed in the early 1800s that each element consisted of identical atoms with a specific weight, and that compounds formed when atoms of different elements combined in definite, simple ratios: 1 to 1, 1 to 2, 2 to 3. This atomic theory revived and refined the ancient ideas of Democritus, but now grounded them in experimental observation and measurement. Dalton assigned relative weights to the atoms of different elements, using hydrogen as the standard with a weight of 1. His values weren't always accurate, but the principle was sound. Each element had atoms of characteristic mass, and these masses determined the proportions in which elements combined. He explained why a given compound always had the same composition, why water was always 2 parts hydrogen to 1 part oxygen by volume, why carbon dioxide was always carbon combined with oxygen in a specific ratio, because compounds were formed by atoms combining in definite whole number proportions. Dalton was colorblind, which he investigated scientifically, writing the first detailed description of the condition. He was quiet, methodical, keeping detailed weather records every day for more than 50 years. He approached chemistry with the same patient observational spirit. accumulating data, looking for pattern, building theory from careful measurement. As the 19th century progressed, more elements were discovered and isolated. Humphrey Davy in England used electricity to decompose compounds, isolating sodium and potassium by passing electric current through molten salts. These reactive metals had never been seen in pure form before. Sodium, soft enough to cut with a knife, shining silver, reacting violently with water. Potassium, even more reactive, bursting into flame when exposed to water. Davy also isolated calcium, magnesium, barium, strontium, demonstrating that electricity could break apart compounds that resisted other methods of decomposition. This electrochemical approach opened new possibilities, revealing elements that had been locked in compounds, showing that chemical bonds could be understood in terms of electrical forces. Jöns Jakob Berzelius in Sweden determined the atomic weights of many elements with remarkable accuracy. He analyzed thousands of compounds, carefully measuring their compositions. He introduced the system of using letter symbols for elements: H for hydrogen, O for oxygen, C for carbon. This notation made chemical formulas much simpler to write and understand. Water became H2O, showing its composition clearly and concisely. Berzelius also coined important chemical terms still used today. He distinguished between organic chemistry, the study of carbon-containing compounds associated with living things, and inorganic chemistry, the study of other substances. This division would prove somewhat artificial, but it reflected observed differences in how these compounds behaved. The discovery of new elements continued throughout the century. Some were found in rare minerals, extracted through painstaking chemical procedures. Others were detected through new analytical techniques, like spectroscopy, which revealed the presence of elements by the characteristic colors they produced when heated in a flame. Cesium and rubidium were discovered this way in the 1860s, identified by the unique lines in their emission spectra before anyone had isolated macroscopic samples. Helium was first detected in the sun's spectrum before being found on Earth. Its name derives from Helios, the Greek sun god. Patterns began to emerge as more elements were characterized. Certain elements seemed to have similar properties. Lithium, sodium, and potassium, all soft reactive metals, chlorine, bromine, and iodine, all reactive nonmetals that formed similar compounds. Investigators began arranging elements in various schemes, trying to find order in the growing list. Dmitry Mendeleev, a Russian chemist with wild hair and an unconventional spirit, made the breakthrough in 1869. He arranged elements by atomic weight, but left gaps where properties suggested elements should be. He predicted the properties of these missing elements with remarkable accuracy. When gallium was discovered a few years later, it matched his predictions almost exactly. His periodic table revealed that properties repeated at regular intervals. Chemical behavior was not random, but followed patterns based on atomic weight and structure. Elements in the same column had similar properties. The table had holes, suggesting undiscovered elements. It had an elegant logic that hinted at deeper underlying order. Mendeleev's table was not immediately accepted, but as predicted elements were discovered and found to match his descriptions, it became clearer that he had found something fundamental. The periodic table became the organizing framework for all of chemistry, a map of the elements showing relationships and patterns. Yet even as Mendeleev's table brought order to the elements, deeper questions remained. Why did elements have these specific properties? Why did the pattern repeat? What determined an element's chemical behavior? The answers would come from discoveries about the internal structure of atoms themselves. In 1895, Wilhelm Röntgen discovered mysterious rays that could pass through paper and wood and even flesh, revealing the bones within. He called them X-rays, marking their unknown nature. These rays emerged when fast-moving electrons struck metal targets, though neither electrons nor their role were yet understood. The following year, Henri Becquerel in France discovered that uranium compounds emitted their own penetrating radiation without any external stimulation. Photographic plates wrapped in black paper were fogged when placed near uranium salts. Something was radiating from the uranium itself, constantly, inexplicably. Marie Curie, working with her husband Pierre in a cold, converted shed in Paris, investigated this phenomenon with intense determination. She coined the term radioactivity and set about measuring it in various substances. She found that the intensity of radiation was proportional to the amount of uranium present, suggesting it was an atomic property, not a molecular one, working through tons of pitch-blende ore. The Curies painstakingly isolated two new elements, both more radioactive than uranium. They named one polonium, after Marie's native Poland, and the other radium, from the Latin word for ray. The work was physically exhausting, stirring boiling solutions with iron rods nearly as tall as Marie herself, breathing fumes, exposed to radiation they didn't yet understand as dangerous. Radium glowed in the dark with a soft blue-green light, its radiation continuing endlessly, seemingly violating the conservation of energy. Where was this energy coming from? The implications were staggering. The atom was not indivisible after all, not a solid, unchanging sphere as Dalton had imagined, but something more complex, something that could transform, releasing energy in the process. Ernest Rutherford, a New Zealander working in England and Canada, investigated radioactive emissions, identifying two types: alpha particles, which could be stopped by paper, and beta particles, which penetrated further. A third type, gamma rays, similar to X-rays but more energetic, was identified by others. Rutherford showed that alpha particles were helium atoms, stripped of their electrons, and that when radioactive elements emitted these particles, they transformed into different elements. Uranium slowly became thorium, which became another element, and so on down a chain of transformations. The alchemist's dream of transmutation was real after all, not achieved through chemical processes, but occurring spontaneously in certain elements. In 1911, Rutherford proposed a revolutionary model of atomic structure based on experiments where alpha particles were fired at thin gold foil. Most passed through, but occasionally one bounced back at a sharp angle. He concluded that atoms were mostly empty space, with a tiny dense nucleus at the center containing most of the mass, and electrons orbiting this nucleus like planets around a sun. This nuclear model explained many observations, but it created new puzzles. According to classical physics, orbiting electrons should continuously radiate energy and spiral into the nucleus in a fraction of a second. Atoms should be unstable, yet they persisted. Something was missing from the theory. Niels Bohr, a Danish physicist working with Rutherford, proposed that electrons could only exist in certain specific orbits, quantum states with discrete energies, Electrons could jump from one orbit to another, absorbing or emitting energy in precise amounts, but they could not exist between these allowed states. This quantum model explained the spectral lines of hydrogen beautifully. The specific wavelengths of light emitted corresponded exactly to the energy difference between allowed orbits. It was strange and unprecedented, imposing discrete jumps where classical physics predicted continuous change. But it matched experimental observations with uncanny precision. The understanding deepened through the 1920s and 30s. Louis de Broglie proposed that electrons had wave-like properties as well as particle-like properties. Werner Heisenberg and Erwin Schrödinger developed mathematical frameworks for quantum mechanics, describing electrons not as particles in definite orbits, but as wave functions, probability distributions showing where electrons were likely to be found. In this quantum world, electrons occupied orbitals, three-dimensional regions around the nucleus. The periodic table's pattern finally made sense. Elements in the same column had similar properties because they had the same number of electrons in their outermost orbitals. Chemical behavior was determined by these outer electrons, their arrangement, their availability for sharing or transferring to other atoms. The chemical bond itself came into focus. Gilbert Lewis proposed that atoms shared pairs of electrons to form covalent bonds, creating stable arrangements. This sharing explained why hydrogen formed H2 molecules, why oxygen formed O2, why water was H2O with the oxygen atom sharing electrons with two hydrogen atoms. Linus Pauling extended these ideas, describing how orbitals could blend or hybridize, explaining molecular shapes and bond strengths. He introduced the concept of electronegativity, a measure of how strongly an atom attracts electrons, allowing predictions about whether bonds would be ionic, with electrons transferred from one atom to another, or covalent, with electrons shared, or something in between. The 20th century saw chemistry expand in every direction. Organic chemistry grew enormously as chemists learned to synthesize complex molecules, creating dyes and drugs and plastics and countless other materials. The German chemical industry became dominant in the late 19th and early 20th centuries, producing synthetic indigo that replaced natural dye sources, creating aspirin and other pharmaceuticals, developing processes for industrial-scale production. Fritz Haber developed a process for synthesizing ammonia from nitrogen and hydrogen, crucial for producing fertilizers and explosives. The process required high temperatures and pressures, with iron catalysts facilitating the reaction. It transformed agriculture, allowing the production of nitrogen fertilizers without relying on natural nitrate deposits, supporting a vast increase in food production, though also enabling modern warfare through abundant explosives. The same chemical knowledge that created fertilizers and medicines also produced poison gases used in World War I, chlorine and phosgene and mustard gas, drifting across battlefields, causing terrible suffering. Chemistry's power was neutral, capable of healing or harming, depending on human choices. This duality would become even more apparent as the century progressed. Polymers emerged as a major field. Leo Baekeland created the first fully synthetic plastic, Bakelite, in 1907, opening an era of materials that didn't exist in nature. Wallace Carothers at DuPont developed nylon, the first fully synthetic fiber, strong enough to replace silk in parachutes. versatile enough to become ubiquitous in clothing and countless other applications. The understanding of chemical kinetics advanced. How fast do reactions proceed? What factors affect reaction rates, temperature, concentration, catalysts? Each variable could be studied, measured, related to the molecular processes underlying visible changes. Arrhenius developed equations relating temperature to reaction rate, explaining why chemical processes speed up when heated. Analytical chemistry became increasingly sophisticated. Instruments could detect and measure substances in tiny concentrations, spectroscopy in various forms, infrared, ultraviolet, nuclear magnetic resonance, each revealing different aspects of molecular structure. Mass spectrometry could determine molecular weights and fragment patterns, providing detailed structural information. Chromatography allowed separation of complex mixtures, components moving at different rates through a medium, emerging separately where they could be collected and analyzed. This technique became essential for analyzing everything from blood samples to environmental pollutants, from flavoring compounds to drugs. The electron microscope revealed structures at scales impossible with light. Viruses became visible. The detailed architecture of crystals could be examined. Later, scanning tunneling microscopes would allow imaging of individual atoms, making visible what Democritus could only imagine: those ultimate particles arranged in precise geometric patterns. Biochemistry emerged as a discipline, studying the chemical processes within living organisms. Enzymes were revealed as protein catalysts of extraordinary specificity and efficiency. The structure of proteins was gradually worked out, long chains of amino acids folding into precise three-dimensional shapes, their function depending on their form. The discovery of DNA's structure by Watson and Crick in 1953, building on Rosalind Franklin's X-ray crystallography data, revealed the molecular basis of heredity. The double helix with its complementary base pairs explained how genetic information was stored and replicated. All of life's diversity ultimately came down to chemistry, to sequences of nucleotides encoding sequences of amino acids that folded into proteins that carried out the functions of life. Chemistry had come full circle, in a sense, from ancient attempts to understand life's essence through material transformation, through centuries of accumulated practical knowledge and theoretical development, to a molecular understanding of life itself, the mechanisms of inheritance, of metabolism, of cellular function, all revealed as chemistry, as the orchestrated interactions of molecules following the same principles that governed simpler reactions in flasks and beakers. Environmental chemistry emerged as pressing concerns. DDT and other persistent pesticides lead in gasoline and paint, acid rain from industrial emissions, the thinning ozone layer. Chemistry had created many of these problems, but chemistry also provided the understanding needed to address them, to measure pollutants, to understand their effects, to develop alternatives. The development of computational chemistry allowed prediction of molecular properties and reaction pathways. Powerful computers could solve the quantum mechanical equations approximately, modeling molecular structures and behaviors. Drugs could be designed on computers, tested virtually before any synthesis was attempted. Materials could be optimized. Reactions could be understood in unprecedented detail. As the 20th century ended and the 21st began, chemistry had become deeply integrated with other sciences, materials science, nanotechnology, biochemistry, environmental science. The boundaries blurred as problems required interdisciplinary approaches. Yet the fundamental questions remained chemical. How do atoms and molecules interact? What determines structure and reactivity? How can we harness these principles to create desired outcomes? And beneath all the sophistication, all the advanced instruments and computational models, the core principles remain those discovered through centuries of patient observation, conservation of mass and energy, the periodic properties of elements, the quantum nature of matter, the relationship between structure and function. These principles, discovered through countless experiments in laboratories, quiet and bustling, in universities and industries, by individuals driven by curiosity or practical need, formed the foundation of our material world. The story of chemistry is not finished. New materials are being created, new drugs discovered, new processes developed. But perhaps there is value in pausing here, in this quiet moment, to contemplate what has been learned, to appreciate the journey from fire to quantum mechanics, from gold-seeking alchemists to genome-editing biochemists, all asking fundamentally similar questions about the nature of matter and transformation. The deeper one looks into chemistry, the more it reveals about the fundamental nature of reality itself. Every solid object, every liquid, every gas is composed of particles in constant motion, vibrating, rotating, moving through space. Even when everything appears perfectly still, at room temperature, the molecules in the air are moving at speeds of hundreds of meters per second, colliding billions of times per second. Yet we perceive only stillness and silence. The water in a glass appears calm, but its molecules are in ceaseless agitation, hydrogen bonds forming and breaking in femtoseconds, a time scale so brief that light travels only a fraction of a hair's width. This hidden dynamism exists everywhere, in the wood of a table, in the fabric of clothing, in the cells of our bodies. Nothing is truly at rest. Everything participates in an endless molecular dance, following the laws of thermodynamics, tending toward equilibrium, yet capable of remarkable organization and order. Consider a snowflake, each one unique, yet each one following the same basic hexagonal symmetry. The shape emerges from the way water molecules bond to each other, from the angles determined by the arrangement of electrons around oxygen and hydrogen atoms, from quantum mechanics to ice crystal geometry, from the invisible to the visible. The connection is direct and beautiful. Or consider the colors we see. The blue of the sky results from how air molecules scatter sunlight, preferentially scattering shorter blue wavelengths. The red of a rose comes from pigment molecules that absorb certain wavelengths and reflect others. The green of leaves, chlorophyll molecules capturing photons and using their energy to drive chemical reactions that build sugars from carbon dioxide and water. Color itself is chemistry made visible. Every hue and shade arising from molecular structure, from the arrangement of atoms and the behavior of electrons. The sunset's orange and red, the ocean's varied blues, the infinite gradations of autumn leaves, all chemical phenomena, all expressions of how matter interacts with light. The energy that powers nearly everything on Earth's surface comes ultimately from nuclear reactions in the sun's core. Hydrogen fusing into helium, releasing energy that travels as light across space, to be captured by plants, to be stored in chemical bonds, to flow through food chains and ecosystems, chemistry and physics intertwined, matter and energy in constant exchange. Even our thoughts and feelings have a chemical dimension. Neurotransmitters crossing synapses, hormones traveling through bloodstreams, proteins folding and unfolding in response to signals. The experience of consciousness emerges from chemistry, from the coordinated activity of molecules in the vast network of the brain. This doesn't diminish the mystery, but rather deepens it. How does chemistry become experience? How does matter become aware of itself? The question brings us back to ancient philosophical puzzles, but now with molecular specificity. We know which molecules are involved in memory formation, which ones create feelings of pleasure or pain, which ones regulate sleep and wakefulness. Yet the gap between knowing the mechanism and understanding the experience remains. Chemistry gives us the how, but not quite the why. Perhaps there is something profound in chemistry's insistence on transformation. Nothing is permanent. Everything is in flux. Iron rusts, diamonds can burn, even gold slowly exchanges atoms with its surroundings. The substance persists, but the particular atoms come and go, replaced gradually over time. Our own bodies demonstrate this. The calcium in our bones is not the same calcium that was there years ago. The carbon in our cells has been cycled through the atmosphere, through plants, through other organisms. We are temporary arrangements of atoms borrowed from the environment, assembled into the pattern of a human body, maintained through constant chemical work, eventually to be returned and redistributed. This view is both humbling and connecting. We are not separate from the material world, but continuous with it. The iron in our blood was forged in ancient stars. The oxygen we breathe was produced by photosynthesis. The water in our cells has cycled through clouds and rivers and oceans. We are made of the world, and we will return to it. Atoms persisting, patterns dissolving and reforming. Chemistry also teaches us about emergence, how properties arise that cannot be predicted from components alone. Hydrogen and oxygen, both gases, combine to form liquid water with properties utterly unlike either element, sodium, a metal that reacts violently with water, and chlorine, a poisonous gas, combine to form table salt, essential for life. The whole is genuinely different from the sum of parts. This emergence happens at every level. Atoms form molecules with new properties. Molecules form cells with the property of life. Cells form organisms with consciousness. At each level, new possibilities emerge, new behaviors, new phenomena that could not exist at simpler levels of organization, and yet the fundamental rules remain the same. The quantum mechanics governing electrons in atoms also governs electrons in molecules, in cells, in brains. The laws of thermodynamics apply to chemical reactions in beakers and to the complex metabolism of living organisms. Unity underlies diversity. Simple rules generate endless complexity. There is something almost musical about chemistry. Harmonic relationships in the periodic table, resonance structures in molecules, the rhythms of oscillating reactions, systems seeking equilibrium, sometimes overshooting and oscillating before settling, like waves gradually damping, like sounds fading into silence. The Belousov's Jabotinsky reaction demonstrates this beautifully, a mixture of chemicals that oscillates between colors, red and blue, back and forth, in waves spreading through the solution, pattern and rhythm emerging from chemistry alone, no life required, just the right combination of molecules and conditions, creating order from chaos, temporarily, before eventually running down toward equilibrium. All chemistry moves toward equilibrium, that state of maximum entropy, of uniform distribution, of no more potential for change. And yet, we exist far from equilibrium, maintained by constant flows of energy and matter, eating, breathing, burning fuel, dissipating heat, creating local order at the expense of increasing disorder elsewhere. Life itself is chemistry kept persistently out of equilibrium. A cell dies when it reaches equilibrium with its surroundings. Life requires difference, concentration gradients, energy flows, the ability to harness these differences to do work, to maintain organization, to repair damage, to grow and reproduce. This is the deep insight of thermodynamics. Order requires energy. Complexity requires work. The intricate beauty of living things, the precise folding of proteins, the replication of DNA, all sustained by energy flowing from high-quality sources like sunlight toward the low-quality heat of the universe. We are all participants in this vast flow, temporary eddies in the stream. And so, as these thoughts settle like dust motes finding stillness, as the images of laboratories and reactions and glowing elements fade into softer focus, there remains a quiet sense of connection to something vast and ancient. The same forces that combined hydrogen and helium in the first stars, that forged heavier elements in supernovae, that condensed matter into planets, that sparked the first self-replicating molecules. These forces continue their work in every breath, in every moment. Chemistry asks nothing of us but observation. It proceeds whether we understand it or not. Rust forms on iron, sugar dissolves in water, wood burns to ash. The universe goes on with its transformations, indifferent to our understanding, yet open to our investigation. There is comfort in this, in the reliability of natural law, in the consistency of chemical behavior. Water always freezes at the same temperature, under the same conditions. Hydrogen and oxygen always combine in the same proportions. The periodic table's pattern holds true everywhere we can observe, on Earth, in meteorites, in the spectra of distant stars. This universality suggests something profound, that the rules governing matter are not local, not arbitrary, but fundamental to the structure of reality itself. Chemistry would work the same way anywhere in the universe. The same elements would have the same properties. The same bonds would form. The same reactions would proceed. Somewhere, perhaps, on a planet circling a distant star, water might be flowing. Carbon-based molecules might be organizing into life. Chemistry working out its patterns in conditions we can barely imagine. The details would differ, but the underlying principles would be the same. This thought connects us to the cosmos, makes us less alone in the vastness. The story of chemistry is ultimately a story about change and continuity, about transformation within constancy. Elements persist even as they combine and recombine. Atoms remain even as molecules form and break apart. The fundamental particles endure through countless rearrangements. We ourselves are part of this story, not observers standing outside, but participants fully embedded in the chemical world. Our bodies are chemistry. Our thoughts emerge from chemistry. Our awareness, in this moment, reflecting on chemistry, is itself a chemical phenomenon. neurons firing, neurotransmitters crossing gaps, electrical signals propagating through networks of cells. And yet knowing this doesn't diminish the wonder. If anything, it deepens it. The fact that matter, arranged in particular ways, following chemical and physical laws, can become aware, can ponder its own existence, can ask questions about the nature of reality. This seems almost miraculous, yet it is simply what chemistry does, given enough time, enough complexity, enough energy flowing through the system. Perhaps that is the deepest lesson, that there is no clear boundary between the living and the non-living, between the conscious and the unconscious, between spirit and matter, only different levels of organization, different degrees of complexity, all following the same fundamental rules, all part of the same continuous reality. The alchemists sought to perfect matter, to find the philosopher's stone, to achieve transmutation. In a sense, we are the transmutation they sought. We are matter that has become conscious of itself, atoms organized into patterns that can think and feel and wonder, the base metal of simple elements transformed into the gold of awareness. This transformation required no magical catalyst, no secret formula, only time and the patient working out of chemical and physical law. Billions of years of stars forming and exploding, of planets coalescing and evolving, of molecules combining and competing and gradually organizing into life, of nervous systems developing and consciousness emerging. And now, in this moment, chemistry continues. Oxygen is being transported through bloodstreams. Carbon dioxide is being released. Molecules are binding to receptors. Enzymes are catalyzing reactions. The vast coordinated chemistry of life proceeds, mostly unconscious, mostly automatic, requiring no deliberate thought or attention. The night deepens, or perhaps it is simply the thoughts that deepen, settling like sediment in a still water. The questions remain, but they feel less urgent now, less demanding of answers, content simply to exist, to be held gently in awareness. Chemistry will continue its patient work, in laboratory and in nature, in industry and in living cells, transforming substances, revealing new possibilities, creating materials that never existed before, solving problems, sometimes creating new ones, always exploring the space of what is possible within the constraints of physical law. But for now, there is just this quiet contemplation, this sense of connection to the material world, this appreciation for the elegant simplicity underlying endless complexity. The periodic table hangs in memory, elements arranged in their rows and columns, each one a thread in the vast tapestry of matter, each one playing its part in the ongoing story. The story has no end, only pauses, only moments of rest between transformations, and in this pause, in this stillness, there is everything and nothing, just the gentle awareness of being, of existing as a temporary pattern in the flow, of participating in chemistry's ancient dance. The words fade now, like the last light fading from the sky, like heat gradually dissipating into the surroundings, like a reaction approaching equilibrium. The story settles into silence, into the deep quiet, from which all things emerge and to which all things return. And there is only this moment, this breath, this gentle letting go.